Hello, everyone. um, Hello, and welcome to Module 5. Module 5, I'm going to revisit. I know I've talked about it before. I'll talk about it again, trying to keep the material focused on the modules that have not been completed. So jumping straight into Module 5, what's it about, right? The short answer is it's all about ensemble methods. So the idea of an ensemble method is that you combine things together in some fashion. And it can be done in kind of two different ways. One of them is around bagging, one of them is boosting. There's probably actually some additional approaches to ensemble methods beyond those two. Those are the two that you generally talk about the most whenever you're kind of getting familiar with the concept. The idea is that you take potentially different, you do different stuff with the data, or perhaps you do something with some different models. And that's the key distinction. So by the end of Module 4, you should be able to develop analytic models using bagging and boosting techniques, also be able to explain the concepts of ensemble methods, be able to map data to graphical elements, visualize spatiotemporal data and higher dimensional data, develop a classification model using bagging and boosting. I think we just said that, and evaluate the performance of said models. So first of all, what's an ensemble technique? Key concept and the basic idea is that it's when you combine things together, a group of things, be it people, software, or whatever. So an ensemble is potentially a collection of people working towards some goal. Ensemble learning is whenever that goal is to learn and to be able to do some sort of quasi intelligent, even potentially modeling of the data, and being able to use multiple techniques together in a way that makes them stronger. The reason is that the more learners you have, the lower the ensemble error. And the basic idea is that you increase them so that collectively they are smarter, is the basic idea. So before we get into bagging, you kind of have to review a bit of statistics, right? Our favorite topic in the world, otherwise you wouldn't be a data science person. But the basic idea here is that the concepts of between with replacement and without replacement. Without replacement means that whenever you take it out and put it into a subset for a sampling perspective, then you don't put it back. It's taken out and it is not able to be used again. With replacement means that it can be drawn and belong to multiple sets, so multiple samples. A key concept because when we're doing bagging with replacement. So you basically take your data set and you pick a set of things from it, and then you may have a certain amount of overlap. It's typically done in a random fashion so that you pick randomly a set of n items to go into a set, and you have multiple ones of those sets, each one of which will be given a classifier, potentially the same classifier, or they might be different depending upon what's going on. But they very well could be the same type of classifier. And then at the end of the experience, you combine together the results of each one of those classifiers through some sort of way of making a decision about something. Since this whole point is to classify, if 2 out of the 3, as you see on the screen, agree that it is something, then probably it's something. So if you're looking at a picture and 2 of the classifiers say it's a dog and the third one says it's a cat, then it's probably a dog. So that's the basic idea, is to be able to basically vote and combine together the results in some intelligent fashion to decide what something should be. And that's very much bagging. So a simple example that's using the sklearn utilities and such to basically walk through an example. The documentation is always a good idea to be able to go and take a look at. I've got the link to it there at the bottom right corner. So and also if you Google sklearn resample, it'll give you a pretty good hint as to what those things are. And so as you can see, it's common enough that it has its own basically page and such. And so that example that you're seeing came out of one of the books that's available to you inside of the O'Reilly collection. So Feel free to utilize multiple sources, and especially as long as you give credit to the sources that you use. Perfectly fine with that. So boosting, a slightly different sort of thing, and it may almost seem counterintuitive. But the basic idea is that you want to improve the accuracy by basically focusing on the negatives. So the things that you didn't get right is the way to think of it. But it may seem counterintuitive because you might think, well, I should focus on the ones I got right so that I get more of them right or something, right? But it's probably closer to, so you take a test and you don't do great on 5 out of 20 questions. And you're given the opportunity to take that test again. What are you going to study? You're not going to study the ones you got right. You're going to study those 5 you got wrong, right? So that's the basic idea here is you increase the weight, and the weight may be instances of occurrence. That's one way of increasing the weight. But you're basically biasing it such that the classification puts greater emphasis on those ones that were missed than it does on those that were right. And it results in better improvement because it does essentially see more of the thing it's not doing as good at, right? And another sort of example, this one pretty simple because it's actually just making a call to AdaBoost, which is one of the classifiers that is very common these days. Again, the documentation on the library and the appropriate parameters that you may be passing in. So again, another example from an O'Reilly book there that you may want to take a look at. Ensemble learning is a significant enough field, obviously, that there's multiple books written on the topic, not just one. It's a field of research unto itself. There are some additional types of boosting techniques that probably pays to know about. Gradient boosting, it's a way of kind of gradually doing it. And I'm reading through here. You train the new model on residual errors. So that's the kind of the basic idea is you figure out the pieces that are left over and you use those as something to do your training on. So as you can see, very similar to the example previously of AdaBoost, because basically it's just creating a classifier with appropriate parameters and then calling cross value score and then getting the mean. In this particular case, didn't do as well, but it may not necessarily mean much because they're on 2 different data sets. Shifting over to deliverable 5, always a good idea to talk about the things that you're being asked to do. You're now a data scientist at a cancer research institution. You're asked to write a program in Python that predicts cancer cells from some imaging. The detailed instructions load the data and then basically reading it in, or load the relevant libraries and read the data. Display the first 10 of the data set, which is kind of a normal thing to do. Use describe to talk about the values of the data. And on the diagnosis column, perform an explicit conversion of categorical features to numeric values using the map function. And then basically do the test train split to set up your testing and training data. And then for the bagging, the AdaBoost and the bagging classifier, for each one of those, create a classifier, fit, make predictions, perform cross-validation with 5 folds, and record errors for each cross-validation run and print it out. Then, taking that information, write a memo that includes a description of the algorithms that are used to perform this computation, the results of data exploration with detailed analysis, and a table containing the performance metrics, along with an explanation of how the metrics affect the results, and obviously your source code. And a brief look at the data. This is a relatively mature data set, not quite as old as IRIS, but it's been around for quite some time. And then the conversion that you're doing here is on this diagnosis column from M and B, which is malignant or benign, converting that to something that is numeric in nature, probably 0 or 1, up to you to decide which is 0 and which is 1. If you're testing for cancer, then I guess 1 would be malignant. But maybe you're testing for the absence of cancer. But anyway, so that's basically the idea of the data, the history of the data set, a brief sort of exploration of it, so you can kind of take a look and see what you're looking at from a visualization perspective. And then where the data came from originally is out of this archive. It was the cancer Wisconsin diagnostic set, so Wisconsin diagnostic breast cancer data set. If you Google that, you'll see it's a thing that's been around for quite some time. And with that, I've reached the end of the discussions. If you have a particular question about the assignment you're working through, let me know. If there's a particular topic that you would like me to speak on, perhaps APA type writing material or whatever, do let me know. I'm here to help you be successful. You're doing great, not too far away from the finish line, but it's always a good idea to try to finish strong. So with that, I'll wrap this up. I'll give you back a little bit of time, and we'll talk again on Wednesday.